I think we can start. And well, it's a big pleasure to introduce our seminar speaker today, Dr. Nancy Levinson. And let me give you a brief presentation of her impressive career. So she did the PhD in California, in Berkeley, and then she was a postdoc at the same place. Then she moved as a postdoctoral researcher to the Johns Hopkins University in Baltimore. And then she got a permanent position at the Kentucky, in Kentucky, the University of Kentucky. Then he became deputy director and head of science at the Gemini Observatory. And finally, she has become the deputy director of the Space Telescope. So I have known Nancy for 10 years, for more than 10 years now, when we both were at the warranty time team of CanariCam. And coincidentally now, CanariCam is starting to observe again in the GTC. And she's here with us this week because we had our GATOS meeting, which is a consortium that we have created for exploiting ALMA and James Webb data. And so we have this opportunity to hear about the work that they are doing at the Space Telescope. So I give you the word.
Thank you very much, Christina. Yeah, it's absolutely my pleasure to be back here. One of the things Christina did not mention is I also had the opportunity to spend a few months at the IAC when I was on sabbatical here. So it's great to be back and to see the other things that are going on here. It's a real pleasure. So I'm going to give you a bit of a whirlwind overview of many of the different things that are going on at the Space Telescope Science Institute, or STScI, or sometimes just the Institute. It's a different kind of a place, and we're involved in a number of different missions. So pretty exciting to see what's going on, and I think it may be interesting for you also with a combination of the research and observatory support that goes on here. I lost my click. I'll do it by hand. Oh, okay, great. So as Christina said, the particular reason that I'm here now is for a meeting of the GATOS, so the acronym Galactic Activity, Taurus, and Outflows Survey. We're largely focused on nearby active galaxies and interested in both the inflow and the outflow of those galaxies. And as Christina mentioned, right now we're using a lot of new ALMA observations, and there's a lot of experience across the team, including both ground-based mid-infrared, so CanariCam has been a key instrument for us, as well as Vizier. And also a lot of the team has experience with adaptive optics near-infrared observations, where we're really taking advantage of the spatial resolution, the genuine physical spatial resolution that we get by observing the nearby galaxies. This is a picture of some of the team from our last team meeting. We don't yet have the photo from this meeting yet, so well, that will be something for the future. Haven't got it. I wanted to tell you a little bit about Space Telescope Science Institute. The reason it was founded was really to be a connection from NASA, which is very good at the engineering and the rockets and putting together telescopes and that sort of thing, to the science. And so the discussions that went on in 1976, before the Hubble Space Telescope was even launched, in fact, before it was named, it was simply known as the Space Telescope, to understand how to really optimize the science coming out of the Space Telescope. And that was where this concept of an independent institute with scientists located in it to be that connection. So providing the long-term guidance and support for the scientific effort, to provide a mechanism for engaging the participation of astronomers throughout the world, and to provide a means for the dissemination and utilization of the data derived from the Space Telescope. And so the institute was established in 1981, again before launch. And it's worthwhile noting that there has been the continued commitment to having this kind of an organization to really maximize the science coming out of NASA's facilities like this. So this was a 2007 report done by the National Academies of Science that was reaffirming this approach, saying that that we really require the participation of the astronomical community, and that as a result have advanced the science far beyond what would have been possible without them, without the scientists involved. And so as a result, we continue to keep scientists very involved directly in the work that we do, that we think that having active scientists with their independent research programs supports the community use of the observatory, that as you've probably experienced yourself, that you're really pushing the capabilities and you know what can be done with the facility, and so you insist on making that happen, and then you can deliver those kinds of opportunities for everyone who has access to the facilities. And so this is one of the recent examples. Adam Riess is an instrument scientist at Space Telescope, as well as a professor at Johns Hopkins University. And so he needs the extreme calibration of the instruments to be able to successfully complete the programs that he's doing measuring the Hubble constant. And this is one of these interesting results showing the tension between the late time or current universe measurements of the Hubble constant and the early time measurements that come from the cosmic microwave background. And so in particular, being able to measure the Hubble constant to this 2% level is requiring instrument calibration at the 1% level, and this is something that he's able to do because he understands the instrument, and then that's fully available to the whole community. And in addition, I'll also point out, genuinely new observing modes have been needed to run these programs efficiently, and again, that's been promoted by the scientists. So just a little bit about STScI as it is. So we're a freestanding research institute. The nonprofit Association of Universities for Research in Astronomy is the organization that actually runs it. We're located on the Johns Hopkins University campus in Baltimore. And right now we've got over 700 staff members, many scientists, but also a large number of engineers, IT, and other kinds of people that we need to really keep things running, including the administration and other kinds of business support work. We're very much a partner with NASA, running NASA missions, and then as a result through the other partners, including the European Space Agency and the Canadian Space Agency that are partnering with NASA. So the major work areas that we're involved in right now, so we do the science operations for Hubble or HST, James Webb Space Telescope, and also looking forward to Jwst, where we'll be the Science Operations Center. And then something that's new for us in a sense is being the Mission Operations Center as well for the James Webb Space Telescope. There's a really strong connection there between the instruments and the operation of the telescope, and so that's the reason to locate this at the Science Institute, as opposed to, for example, the way we operate Hubble now is that the mission operations are run out of a NASA center, out of NASA Goddard. We have a very strong archive program, and so the archive then is also introducing lots of data science and the sort of community collaboration that comes with developing the data and the data tools with the community. We have a strong outreach program where there's the side of outreach to the scientific community so that people can understand how to use the facilities, and also to the general public. And a lot of our scientists in particular are looking ahead to the future to what kinds of missions and facilities may be coming, and developing the technology and the science cases for those things. And then, of course, astrophysics research that goes on. I know people tend to be interested in this, so I do have a slide reminding us all of how Hubble is doing. And a key point is Hubble is doing really well. Hubble is operating well now, and we are looking forward to operations into 2025. So there is a long lifetime ahead. Things are operating normally. We currently have 4 science instruments that are in full use. It's a bit of a reminder that it's now been more than a decade since the last Hubble servicing mission. So things are continuing there. The science productivity remains high, and again, that science productivity is a result of the efforts of the entire international community. What we're looking at on the chart here is the number of publications per year, and so now exceeding 950 publications per year. So maybe this chart goes through 2018, so maybe this year with a little bit more we'll hit over 1,000. But one of the really exciting things is that green section in the chart is showing the purely archival publications. That is, the authors had nothing to do with the original proposing team, no overlap between those teams. But making the reduced data available in the archive, possible not only to find but to use directly, means that there's tremendous reuse of all of the observations. And so now that's actually the majority component. Combined with the blue section listed as GEO, that's the original proposing team that did something, and also some are combined, that proposing team also used a bit of archival data. And our librarian is extremely good at identifying the source of the data and understanding the publications, and so there's a small fraction still that's simply listed as unassigned where we haven't been able to identify that fully. The scheduling of Hubble continues to go well. We continue to maintain relatively high efficiency, although constrained programs are getting to be more popular, occupying a bit more of the time. So we get extreme timing constraints, for example, with exoplanet observations that need to be in a particular phase of the observation. Targets of opportunity also, we're getting to have more of those and want to be able to support some of the exciting new things with multi-messenger astronomy with gravitational wave measurements. And so those challenge our efficiency, but are possible in many ways. As I said, we're planning for operations into 2025. The predictions, and of course these are always predictions, subject to reality, but expecting a greater than 80% reliability of all the subsystems through that point. So that's why we really are looking ahead to a strong science program. Recognize, though, that we do face anomalies. Hubble's looking forward to its 30th birthday next year in April. And things do go wrong, so we work hard to get back on track quickly when that does happen. But just recognizing that is a bit of a challenge as we go forward. One of the exciting new things happening with Hubble is there's a new large director's discretionary program called Ulysses. The acronym I have to remind myself because, of course, the trick was to make the nice acronym. It's Ultraviolet Legacy Library of Young Stars as Essential Standards. So this is to develop a spectroscopic reference sample of both high mass and low mass stars, looking over the first 10 million years of stellar evolution. The whole program will take about 1,000 orbits spread over several years' time, and looking at a really broad range of parameter space. So with the high mass stars, looking at spectral type, luminosity, metallicity, and then with the low mass stars also adding particular properties like accretion rate into the study. All of the data will be immediately public. All of the data will be fully reduced. There's a very active team at the Institute working to develop that. Right now, they're busy making the final target selections, and the first observations will begin next year. So looking forward to that. A little bit about the James Webb Space Telescope, or JWST, or Webb, as I say. So a 6.5 meter telescope. Collaboration with NASA, ESA, and the Canadian Space Agency, heading out to L2 orbit. An extreme summary of what's available with the 4 science instruments here. The short point is it's a wide range of imaging and spectroscopy modes that are available. Lots of exciting complexity with things like multi-object spectroscopy, coronagraphy, et cetera. So lots of exciting ways to use the facility, to use the instrumentation. It's not just about having a nice big telescope out in a good location. There's been some great progress coming along with the observatory itself. So these are a couple of images taken from the last cryovacuum test. So this was the last stage of the environmental testing of what we're looking at here is the spacecraft itself and the sun shield all folded up. So the slightly purple color in there is the sun shield. So folded up going into the vacuum chamber, and you can see over on the right-hand side, it lifts up from the bottom to go inside. And this is really impressive and large, even when folded up. So the human beings that are for scale there really give you a sense of what this is. This image is showing one of the tests with a secondary mirror deployment. So there are just a number of exercises and tests that are going on. I should have mentioned all of this is now out at the facility of Northrop Grumman in the Los Angeles area in California, where this is happening. And then a really exciting milestone that's happened recently is the integration. So previously there were essentially two large parts of Webb. There was the spacecraft with the sun shield, and then there was the telescope with the gold-plated mirrors that you can see there. The instrument packages on the back side of that telescope. Those had been two separate pieces, and now they are integrated. So this was NASA's publicity photo that they released of this. So it's a slightly odd configuration of the sun shield, partly folded up, but now we have one observatory. There are more tests to come. There's more work to do, but this is a really exciting milestone along the way. One of the things for us as scientists to be prepared for is we're going to have to wait for a while after launch scheduled for the end of March 2021. We'll have to wait a while until we actually get to use this facility for our science because there's a 6-month period of commissioning. So getting out to the L2 point isn't so much what takes the time. Then there's the gradual cooling of the instruments to be able to begin the observations with the segmented mirror. As you're familiar with GTC, you have to align, you have to phase, you have to get your mirror and telescope working well. And then the actual instrument commissioning, which will be in active phase. So all of that will be about 6 months before we'll see those science images coming. This is an image from our Mission Operations Center. So just to get a sense of it, it is like most Mission Operations Centers that you've seen or seen pictures of before. It's a lot of computer screens, room for lots of people to all be looking in the same direction. One difference maybe is this is one of the nicest ones. There are windows that look to the outside. So I hope people will enjoy that a little bit during some of the time they're there. But now this is already a very busy and active place for us. There are a large number of exercises and rehearsals and getting the teams ready both for normal operations that they'll have to go through and also to be prepared for anomalies, to be prepared for what may go wrong or different is the other way. All right. Some of the things that are very important to scientists looking ahead is our science timeline schedule. So I had mentioned we're looking ahead to launch and commissioning out there, but we can't have the science program be the thing that's slowing us down or limiting us. And so we need to settle on the science program for the first year of operations early. And so that's why we're back here, looking very soon these are US format dates, so looking at towards the end of January next year, where the cycle 1 call for proposals will be reopened. And so that's the open observing call, the general observer call will be open then with a deadline expected at the beginning of May. We are planning for a long period of time allocation committee because we do expect a lot of proposals, and so we want to have enough committee members to evaluate all of those. So that will happen in July and August, and then looking towards the end of August to be able to announce what the General Observer full science program is. Along the way, there has been some time allocated already. The guaranteed time observers, they have put in their proposals and their targets, and so those are all known and available. Obviously, we don't want to duplicate any targets, and so you can see what those are now and see what the observing modes that they're using are. There's also a program, the Director's Discretionary Early Release Science. So those programs have also been awarded already. Those are community-based programs. The data will become available immediately, so public immediately, to give the whole international community a chance to see some data early. And also those teams that are established now have some responsibility to help with the training, help with the understanding, so that everyone can use Webb effectively. So those teams, as I said, are active now. So that's what's happening on the JWST side. What I and the Gatos colleagues that we all were discussing recently is how much else is happening at the same time. So the usual Hubble cycle is coming up around the same time. So the Hubble cycle 28 call will be a little bit earlier than usual if you've been following those deadlines. But cycle 28 will be coming up again the beginning of next year. ALMA will have a deadline and their TAC will have to meet. ESA will have a deadline in there. Chandra's another one that we pay attention to, and so they'll be in there. So it's going to be really busy if you use many of these facilities. So plan ahead. And start working on your proposals early for multiple reasons. So one, okay, you're going to be busy. You're all going to be extremely busy in the spring next year. But also, JWST is a complex proposing process. It's single stream. You're putting in your entire observing configuration at the beginning. We recognize that it's a pretty steep learning curve to use some of the tools. You do need to use the electronic astronomer's proposal tool to be able to propose. You do need to use the exposure time calculator to calculate your sensitivities and so on. And these things do take a while to learn how to use. So give yourself time to do that is an important point. There are lots of things that we are doing, we at the Institute are doing to help support you. So I'm mostly mentioning those. There also is ESA support available, but all of the Institute things are available to everyone. So some of the resources we have, this is from our web page with the web address is listed there. This is the observer, the scientist site. So we have a regular observer news feature. You can either check in and get those things as they come up. You can sign up to get a digest of those notices every couple of months. There's also a resources section, which that will take you to more information in detail about, say, the instrumentation or the proposal planning tools that you'll need to use. So that's a really good central place to start and get and look at things. These are a couple of specific things to look at. There is a help desk. And so help desk useful in multiple senses. Of course, you can ask your questions and you'll get an answer back, but there's also a knowledge base associated with it. So everyone can see questions and answers, and that remains searchable. So that's a good tool to use. Not only can you see what other people are doing, but your questions will then be answered, and that will be available for everyone to see, because chances are many people will have the same kinds of questions. There's a full documentation system. We call it JDocs. It's a little bit like Wikipedia is how we think of it, that you can drop in anywhere and get started and move around. It's not designed for a strict linear format. One of the things For those of you who had followed, there was an original call for proposals that was then canceled. We learned a lot from that experience, and we've put that into practice. And so we've refreshed a lot of the user documentation to help get people to what we think are some of the key sites that they will need. Also, another piece of things comes through videos. So the JWST Observer YouTube channel is pretty active, and I'm not sure how well you can read these from the back of the room, but they're both high-level introductions to things, so that top listing is just the beginning of the overviews of the different tools, the different observing process. But then, for example, when you get into that exposure time calculator, there are lots of distinct exercises to go through to learn about that. So that's another place to check things out. And then, of course, social media still is a useful place for things. So besides YouTube, there is a JWST Observer Twitter and Facebook account that you can follow for news. One other thing to note is we've already established the JWST User Committee, and so that's a place where you can where the user committee is representing you, us as users, all of us. So to raise your concerns to them, and they're actively working. Something else that's coming up is the plan for the Institute to produce a number of webinars during the proposal cycle, so releasing one a week between January and April of next year, intended to be timed for what we hope the phase of the proposal process people will be in. But there are also a number of local classes going on, and ESA is supporting the training of people in the European community. And so, in fact, there will be local classes here at the IAC in March. So that will be another good opportunity. All right, that's what I had to say about JWST. Switching gears a little bit. Maybe, if this will start, yes. I want to talk about WFIRST. So WFIRST, looking beyond JWST, it's a Hubble-sized mirror, so we'll get the same kind of spatial resolution and sensitivity, but over 100 times the field of view in the main wide field instrument. STScI is the science center for WFIRST, and so it will be a really exciting opportunity for survey science from space, but also for more detailed scientific observations. So these are Hubble observations of Andromeda, but it gives us the sense of what we will also be getting on a regular basis from WFIRST. This kind of richness in the fields, this kind of detail that we'll be seeing. But the difference is, of course, just the much wider field of view. So you get here a sense of how Hubble completed these observations, which was with over 400 separate pointings to be able to tile over the field, and then WFIRST can cover that in two. So what was an extremely large Hubble program, a large effort for both the proposers and a legacy for the community, will be absolutely normal for WFIRST sorts of observations. So really being able to apply that survey power, we've seen it from Hubble in the nearby cases, but of course also WFIRST will be looking on cosmological scales for further studies of dark energy and dark matter. So this is another sort of example. Now we're looking at M33, then not so much focusing on individual stars, but some of the other sorts of detail to be able to get when you can look at more nebulous objects or globular clusters, or even catch those background galaxies that are hiding in the field. So the very straightforward and easy thing to see is that simply with the larger field of view, you get to see more at the same time. But actually, WFIRST will be much more efficient than Hubble for observing large areas. And so making the calculations, looking at some of the large area fields that had already been observed, in some cases, WFIRST will actually be 1,000 times faster at completing those kinds of survey observations. I'm mentioning the wide field instrument partly because it's got a very broad scientific instrument and it's very easy to understand the developments that will happen with that. There is also a coronagraphic instrument. It's intended as a technology demonstrator, but it will be exciting to have a powerful coronagraph flying in space. So just mentioning a few of the different kinds of science cases that might be done. For example, looking at nearby galaxies instead of these special exclusive cases, now we'll be looking at 100 nearby galaxies, being able to do the kinds of galactic archaeology by looking at the stellar populations in detail, looking at the stellar populations themselves for initial mass functions or stellar feedback, and then really testing those galaxy formation models over large-scale time. So there are a number of different ways that WFIRST will bring open science opportunities to everyone. So that all of the data, first of all, will be immediately public. There's no proprietary or exclusive access period to any of the WFIRST observations. So that will be available to everyone. There will be guest investigator opportunities to design your own program, look at your own favorite patch of the sky, whether it's a galaxy or otherwise, as well as getting information from the surveys. And then there will also be a strong archive and a very rich archive with a lot of data from WFIRST. So this really is a complementary program that in some cases we can think of JWST as the telephoto lens zeroing in on some deep specific observations and getting the wider fields from WFIRST, building on a lot of what we've already learned from Hubble. Something else, something different going on at STScI is our archive. So we call it the Mikulski Archive for Space Telescopes, or MAST. MAST is the place that many users, especially US-based, go for their Hubble data. Hubble's actually a pretty small fraction of the archive these days. We support over 20 missions in the archive, and right now, pan-stars, these yellow circles are scaled for data size, and pan-stars, a ground-based all sky to the extent that it could be observed from Hawaii, is really the largest case. So MAST serves as one of three regular astrophysics data archives, and we primarily support the UV, optical, and IR, but also do have a number of other ones, and we're open to supporting all wavelengths. It's important that the data are actually in the archive are actually processed, that they're ready to use, they're not just raw data. And then there are also a number of high-level science products, some of them produced by the community with their important work, and then leaving those high-level science products back in the archive, and some of which have been produced by the Institute. So I mentioned pan-stars with the ground-based data, and so this is the survey map of pan-stars, and has recently had the second data release. TESS is another really exciting thing that we're supporting. So that's a small it's an Explorer mission from NASA, primarily thought of as an exoplanet observer. A little bit, you can think of it by analogy with Kepler. But there again, we've got the data as well as the supporting tools to be able to use that, and we've hosted a number of workshops for that. I'll mention that some of the things that we have in MAST also correspond to what's in the ESA archive. So for example, the Hubble Catalog of Variables, that's an ESA product that we're also serving up through MAST. We do try to be a lot more than serving up just bits of data and providing some more specialized interfaces that can help with the science. And so this is an example we call this exomast. This is the useful interface if you're interested in exoplanets, right? Exoplanets, you really care about phase. You don't just want to know what's been observed. You want to know when it's been observed, not just in absolute time, but how it fits in with the orbit. And so this is something that shows the observations, in this case, some Kepler observations, some Kepler full field, and also some Swift observations as a function of the phase of this particular planet. In this case, this is Kepler 185b. So we hope that providing these kinds of science-motivated interfaces, then people can get more of their own results out quickly. All right, another piece, another different thing going on at STScI is outreach, and here now I'm focusing a bit more on the public outreach, where we do broad outreach for all of the missions that we support. And it's really great to be able to have the science motivation, the science foundation in what we do. So we're not just trying to identify things that will be popular for the public, but by working with the scientists in the community, as well as, of course, designers and writers and others, to get out the correct and informative story, but that's still very, very engaging. And so we have a large team that works on this collectively. As I said, that we build these assets, these products, these things that people will look at for engagement and information. We also find then that the Institute is a trusted source. We don't publicize everything that's related, and so as a result, the news media are comfortable picking it up and believe that what we're offering is important and useful. And so this is an example of the reach. This is worldwide reach, specifically for the case of Hubble releases, and we're looking over last year. This is how many millions of readers were likely to have seen some of these results. So again, one of the things I think is really exciting is that the public absolutely picks on the science results. Is that they're not just looking at the things that are pretty pictures, but that they really are interested in, for example, learning about the first exomoon or galaxy surveys that have been released. We also learned from this that they really care about Hubble as a telescope. And so when Hubble went into safe mode towards the end of last year, that was also one of the most popular releases. Now, unfortunately, there was not a similar peak when we announced everything's great, back to regular operations, it's all good. But at least they were concerned enough to follow on that one. And I will say this is something that has good collaboration with our partners. ESA also maintains a news office, and we do collaborate, and these results ultimately come from all of us. Something else that we're involved with is we have a separate program called the Universe of Learning. So it's not specifically about the information that's coming out of our missions like Hubble or Webb, but broad-based, looking across all of NASA astrophysics. And so in this one, we're partnering with a number of other institutions to get a really broad multi-wavelength view. And so I didn't put the website up here. This is viewspace.org. That has this material that's available. So this one, looking at the right. So on the left-hand side, of course, we get the gorgeous Hubble image of this. But on the right-hand side, you can actually learn something and play around by adding different amounts of, in this case, lots of X-rays to see what the region looks like in X-rays. So these are genuinely informative as well as pretty images to be able to look at. And then one other thing that's going on at STScI is we have an optics lab, the Macedon Optics Lab, that really is one of the world's top facilities looking ahead at high contrast imaging, in particular developing techniques for high contrast imaging for segmented telescopes. So that's something that we want to see looking ahead to the future, and we want to develop this technology now. What we're looking at here, so on the left-hand side, that's some people working in the lab, and then on the right-hand side, this was at the American Astronomical meeting at the beginning of this year, they have a tabletop version of their coronagraph that you can actually move the mirrors, make changes, and see how the coronagraph works. They are making a lot of progress with the coronagraph, and so what we're now looking at on the right-hand side here is an image from the test bed in the lab. It's an ambient atmosphere that they are able to get the significant dark zone, and so here this is the 10 to the minus 6 contrast. But things have been moving along. Oops, sorry about that. There we go. Things have been moving along to get essentially factors of 10 improvement. In this case, what we're looking at now is with a monolithic mirror, not a segmented mirror. They've got the segmented mirror model now and are working with that and working on optimizing that. So that kind of hardware, some of the reason to try to make these advances right now is to be able to look ahead. And we are looking ahead to what may be the new great observatories from NASA that will need some of this technology. So a bit of context for this. The US right now is engaged in the Astronomy and Astrophysics Decadal Survey, sometimes called Astro 2010, where NASA and the National Science Foundation and the Department of Energy, who are our key funding agencies for astronomy, have asked the National Academies of Science to conduct this effort and help us identify our priorities. But NASA has put a lot of effort into the preparation already by funding 4 distinct study teams, so science and technology definition teams is what they're called, to look at 4 concepts so that they can be somewhat mature to be able to evaluate them to be more than simply a good idea about what kind of facility we might like to have in the future for a large space mission. And so these are the 4 concepts. LINX is an X-ray observatory. HabEx is concentrating on being able to observe habitable exoplanets. LUVOIR is a large ultraviolet optical infrared surveyor, so general astrophysics and also to be able to observe exoplanets. And then Origins Space Telescope, which is a long wavelength infrared mission. So these flagship sorts of missions really support science at all scales. That's what STScI has been very involved with, to be able to deliver to a large community true open access, true support for your own science to be able to really optimize the outcomes from these observatories. Individual staff members from STScI have been involved actually in all of these missions. One of the co-chairs of the Origins, Margaret Meixner, is at the Institute, and we've had significant involvement in the others as well. The one particular one, though, that I want to follow up on a little bit is LUVOIR, because that one in many ways is a natural successor to Hubble and even Webb in a certain way. And so this is of course a model for one of the large options for LUVOIR, which would be a 15-meter segmented telescope that really provides incredible resolution and light gathering power for studies. And I find the simulations really convincing to get a sense of what kinds of developments may be coming. And so in this case, we're looking at a redshift 2 galaxy. Here we're looking at the Hubble image of it. It's a low mass galaxy, so high redshift but low mass. So looking back pretty early in the universe, there's a lot you can do with Hubble. There's a lot of science that you can derive from this. But if you get to look at it with a 15-meter aperture, it's really spectacular, and you really begin to appreciate the details and get into the detailed physics of what's happening in this galaxy and how galaxies evolve and how stars evolve at the time. So that's one of the exciting things that I hope that eventually something like LUVOIR is truly part of the NASA program. And then the other side, besides distant galaxies, this is another LUVOIR simulation, but this is imagining what we would be looking at for our own solar system at a distance of 13 parsecs to realize the kind of detail that we can get, not only identifying planets, but genuinely beginning to characterize them. So those are some of the exciting developments I hope we have to look forward to in the more distant future. In the meantime, at STScI, we're busy and happy working with Hubble, getting ready for Webb, and also looking forward to WFIRST for a mid-2020s launch. I will stop there and take questions.
Hi. So you have talked about future instruments for optical, infrared. What about gamma rays? Anything successor for Fermi or?
So I admit I didn't talk much about that because it's not an area that STScI is very involved, but there are NASA Explorer missions that some actually genuinely in development coming on that, and unfortunately I'm just not sufficiently qualified to tell you exactly what the status of those things is. But yes, NASA is still working at high energies, absolutely. Yeah.
Hi Nancy, maybe this is a bit of a technical question on WFIRST, but I was wondering about thinking as regards the astrometric performance on WFIRST. Will that be similar to Hubble, or because it's a much larger field, and I would imagine calibrating across that huge field may be a challenge?
So I think that's exactly it. That the expectation is that the astrometric performance does need to be there, and that we will simply have to do the calibrations to get there. So that's one that I don't remember the immediate details off the top of my head of exactly what's expected. But I think simply recognizing that's a challenge that we have to be up to make good use of the data. Yeah, certainly good that we've got Gaia there as an excellent reference to. Yeah. Right. Okay. So that's something for us to keep track of in terms of that kind of science delivery. I didn't say that some of the model of how WFIRST will be supported is as the Science Operations Center, we at the Institute won't be responsible for absolutely everything end to end, but that there are already some very engaged science investigation teams, and the idea is that we'll be able to use their expertise and what they've learned. We may be the ones to process the data according to their algorithms, for example, but it's not all in-house. It's actually a much smaller effort for us than Hubble is.
So do you think the next call, the next proposals for JWST are going to be very different from the previous call, in the sense that the actual technical aspects of how you prepare the proposal? Because we did prepare a proposal last time that we have ready, but but I wonder if you think it's going to be very different.
Yep. So the overall expectation is that technically it should be very similar. There aren't going to be significant new, say, capabilities, as in like entirely new instrument modes, for example. All of the tools are being updated, so there are minor changes there, and things will have to be updated. One of the specific things that is being updated is the timing model. So the estimates of the total time that programs will take will change. The overall estimate for observatory as a whole is we think we'll be able to be getting something like 10% greater efficiency out of the whole observatory, but individual programs, it will actually depend on what kinds of observations you're making, whether you might wind up seeing this as an improvement or not.
Can you comment on the funding situation of WFIRST?
That's a great one, yes. So the US Congress is extremely supportive of WFIRST. And so a little bit of an aside of American politics, Congress actually has the money and they get to decide how to spend it. So WFIRST has been challenged because the president's administration has put in zero budgets for WFIRST the last 2 years until Webb is complete. But Congress says we want this program to continue. We know that stopping it will only make it more expensive and more difficult in the future. And so Congress has been funding it sufficiently. So the last 2 years, the 2020 fiscal year budget isn't final, but both the House and the Senate have put in what they need. That said, Congress are also very clear that this has a budget cap. $3.2 billion. They don't want it to be more expensive than that. I believe it is possible to do an exciting mission for that, and so we on the science and engineering side have to make sure that we're living within that constraint. So overall, that's where we are, and then we may be able to have even more contributions with partners to develop more there. You're welcome. My pleasure. Thank you.